nanohub.org.
Online simulation and more for nanotechnology.
So, well, as I mentioned, folks, this is actually could be considered as a course within a course. So it's more or less independent. So what we did so far, we covered some fundamentals related to this area. But within this following 9 short lectures, I'm going to overview these areas of interrelated areas of metamaterials, nanophotonics, plasmonics, as well as a bit of quantum photonics. And we will start with metamaterials, and later we consider transformation optics and metasurfaces, these 3 closely interrelated areas. So meta, as I mentioned already, in Greek means beyond. So when we say metamaterials, we basically imply that, by the way, is mic on? Mm-hmm. We imply that we create engineering, design and engineer materials which have properties going beyond of materials which Mother Nature provides. So that's sounds quite ambitious, and to build up on this, I could say that arguably metamaterials is one of the most exciting developments in the areas of optics and materials, or at least in the areas of these optical metamaterials, because it's provided lots of new ideas. And hopefully, as the title of this lecture says, it would be in the basis of technology of the future. So that's what we're going to describe within these first 3 lectures. So we will firstly provide some introduction to metamaterials, and we will distinguish 2 subclasses of metamaterials. Electrical metamaterials, that's pretty much plasmonics. As I said, there is a little bit confusion, if you wish, about using different terminology, basically pretty much about the same field. And depending on the taste of a particular researcher, some people imply a little bit different things when they say plasmonics, nanophotonics, and metamaterials. So I will use these electrical materials, and I'll explain what I mean by this, pretty much in the same context as I use the word of plasmonics. So then I say a few words about magnetic metamaterials, that when you control magnetic properties of materials at optical frequencies, and say how it's related to something which really one cannot find in nature, materials with negative refractive index. And that's actually quite exciting because it's very much different from what we know about conventional optics. And then I say a few words about applications, and one of arguably most exciting, at least this is the applications which launched to a large extent this tremendous interest to the field of metamaterials, and that's related to so-called SUPERLENS, so the idea of super imaging when you could resolve details much more than the wavelengths. So, and in a couple following lectures, I'll discuss things related to transformation optics in one of the most exciting applications related to this clocking, and I'll end up with 2-dimensional metamaterials, or metasurfaces. So, well, the whole idea of engineering to engineer optical properties of materials is based on the fact that when light interacts with materials, it's basically what matters is what light pursues as atoms. And in principle, since the wavelength is rather large, it's, let's say, if you're speaking of the visible, it's 0.5 micron, telecom, it's 1.5 micron. So it means that you could actually design your artificial atom, or meta-atom. And that light would still perceive it as something, as like a unit of your material with which it interacts. So, and that's the whole idea, as illustrated here. Let's say this is the wavelengths, and this is my atoms, which is shown with these squares. And of course, all conventional materials consist of, if I could say so, natural atoms. But the natural atoms are really tiny, only 1 or few angstroms. I could build somewhat larger structure, let's say on the scale of 1 or 5 nanometers. And for light, it still would average out over many of such artificial atoms. So, but then it would see this material as something built of different, designed and engineered artificial atoms, meta-atoms. So, and like here I point inside like 50 nanometers, but in principle it could be 5 or 10 nanometers. And still, since the wavelength is much larger, it would be like new material built out of different artificial atoms. And therefore it would have different properties. Of course, this meta atom still built of conventional atoms, but we build it in such a way that they interact with light in a different way. And as a result, the whole material interacts with light in a different way and provides new properties. That's pretty much the idea. So, and that's what people believe wrote to new optics and new technologies. Well, if you would like to put different types of materials in the context of optics on this size scale, size axis, so we could distinguish 3 different classes of materials. One is, we could call it geometrical optics. In this case, you build your optical elements out of pretty large structures, such as lenses, or let's say mirrors. And in many cases, you actually could describe properties here by using simple geometrical optics, simply because your optical elements are so much larger than the wavelengths, so that unless you're interested in peculiar things like interference or diffraction, you actually could quite often use geometrical optics. Very interesting properties occur when you have the size of the structural unit comparable to the wavelengths. And that describes this phenomena like diffraction. You remember this diffraction grating, interference, and of course photonic crystals belong to this particular class of materials, because the requirement for photonic crystals at the latest period matches the wavelengths, or close to the wavelengths. And as a result, we have these beautiful properties when you have these forbidden energy bands or band gaps. And because of that, you could develop this wonderful materials such as cavities or waveguides, which are comparable in size to the wavelengths. And when we speak of metamaterials, at least in its original definition, we imply that these materials are built of sizes much smaller than the wavelengths. As I mentioned already, sometimes people combine these photonic crystals and metamaterials into one class and still call it metamaterials. But still there is a distinct difference in the, strictly speaking, when we speak of metamaterials, the size of structural units should be much smaller than the wavelengths. Well, and this is a very useful plot which shows dielectric permittivity epsilon and magnetic permeability mu. And of course, both these quantities could be positive or negative. And depending on the sign of these two quantities, we could speak of different regime of interaction with light. Let me explain it in more detail. I believe, by the way, it was Sir John Pandry who first brought this plot, and that really helps to understand different classes of metamaterials. Well, but let me remind you first this formula from the textbook, that refractive index is basically a square root of product of dielectric permittivity and magnetic permeability mu. That's important for understanding of what follows. Dielectric permittivity epsilon characterizes how strongly light couples to the electrical field component. So basically, remember that displacement current E is equals epsilon E. So it shows actually how responsive material are related to the driving force, to the electrical field. And magnetic permeability characterizes the magnetic response of material. Magnetic induction B is equal mu times H. So again, it shows how material responds to the magnetic field component in this case. So you could think of this electrical and magnetic field components as two hands with which light probes atoms in materials, and epsilon and mu are characteristics of this coupling, how strongly light couples to atoms in materials and to material in general. So normally most of materials in terms of optics belong to this class, transparency of dielectrics. Not all, of course, but one could say most. And in this case, both epsilon and mu are positive, meaning that the response of material kind of follows in phase or close to this to the electrical and magnetic field component. So both epsilon and mu positive, and if they are both positive, the product of epsilon mu, of course, is just a positive number, and we know that square root of a positive number would give you get another positive number. So refractive index is just a real number, and light propagates through such materials with some phase delay, but with no much losses. By the way, for now, we assume that losses are very small. We are not focused on losses. Of course, they are important, but what I am about to say, it's more like about the real parts of epsilon and mu. Even though, of course, we understand there are always some losses, meaning that there is imaginary part in the epsilon, mu, and in the refractive index. So that's a large class of materials such as glass, water, and many others. So light propagates through such materials with some phase delay. This phase delay is described by the refractive index, which is again a square root of the product epsilon mu. So there are materials where epsilon is negative and mu is positive, and we are well aware of these materials. This is so-called plasmonic materials, and they're very important because they allow to couple light down to nanoscale. That's in the heart of plasmonics. When epsilon is negative, you could excite the surface plasmon resonance, which enables bringing light down to nanoscale. But if you have a product of negative number, epsilon, and positive number, mu, the product of epsilon mu is a negative number, which means that square root of a negative number would be imaginary, right? Square root of -1 is equal I, which is... and that means that your material becomes absorbent, or let's say it expels light. So it results in these evanescent waves. And that's exactly what metals are. Light does not propagate through metals, it's expelled from metals. And that's simply, you could say, because refractive index is purely imaginary in this case. Of course, there is a counterpart of this in principle. When mu is negative but epsilon is positive, so the so-called magnetic plasma, when epsilon is negative, mu is positive, we call it electrical plasma, and when you have the opposite situation, when epsilon is positive, mu is negative, we'll call it magnetic plasma. But I should say right away that when it comes down to the optical frequencies, we don't know materials, at least occurring in nature, where mu would be negative. As I mentioned already, at optical frequencies, all materials are pretty much almost non-magnetic. Magnetism is very small. So therefore, I put here no naturally occurring at optical wavelengths, even though, of course, such materials are possible. And in this case, light would interact in the same way, meaning that it would not propagate through such materials. It would be exponentially decay, simply because, again, epsilon mu would be a negative number, and the square root of negative number is purely imaginary. We could envision easily that epsilon and mu both are negative. If both are negative, the product of two negative numbers is a positive number, which means that refractive index would become a real number, and means that light should be able to propagate through such a material. And that's exactly what we call negative index metamaterials. They do not occur naturally. There are no materials which, at least we don't know them, where at optical frequencies both epsilon and mu would be negative. Of course, there are materials where epsilon is negative, simple conventional metals. But as I pointed out, that for conventional materials, mu is close to 1 at optical frequency. So you have to design and engineer these materials where epsilon and mu would be both negative. And you should expect that in this case, light would propagate through such materials.
So metamaterials must be both epsilon and mu are negative? Or it can epsilon be negative and mu like equal 1? I mean, we can call the metamaterial. The notation of metamaterial.
So the question was whether for negative refractive index, both epsilon and mu are required to be negative.
So this is the case of metamaterial, or I can call the second and the third and fourth cases?
In principle, we call all these classes metamaterials if they design and engineered. But there is a special class of metamaterials which we call negative index metamaterials. But that's actually a tricky question because metamaterials pretty much to a large extent were started because of this idea of negative refractive index. And when people realized that there is materials with negative refractive index, they started to call them metamaterials. But now we use these metamaterials in more general way, basically when you design and engineer materials. And in this case, you not necessarily have both epsilon mu negative.
I see some people work at optical frequencies equal mu equal 1 at this case.
Right.
So do they consider epsilon equal negative when we use this one?
Right, and you still could call it negative refractive index, but that you would not. But in this case, you shouldn't expect to have a negative refractive index. You still would call them metamaterials, but it's not negative index materials. Yeah, as I said, there is a little bit, let's say, flexibility or whatever, not well-defined term for metamaterials. It depends on, quite often on the interest of a particular researcher. But generally speaking, design and engineered materials with new properties. So we'll start with this quadrant when epsilon is negative, and that's what we call electrical metamaterials. Even in this case, mu is equal 1, if you speak, or close to 1, if we speak of optical metamaterials. So, and that's what I call electrical metamaterials or plasmonics, and I already pointed out this is a route to nanophotonics in the sense that plasmonics enables bringing light down to nanoscale. So I already showed this slide because it's very important in terms of this information processing, how fast you could do this. Here I'm showing the speed with which you could process information, and here a typical size of structures used to process this information. And in that regard, in the past, of course, these devices were large and slow, and with semiconductor electronics, which a major way to process information nowadays, you have very tiny structures, like the size of a transistor is only 4 nanometers, whereas speed is still limited, because with electronics, you could process information indeed quite fast, but not faster than, let's say, 100 gigahertz, or 10 to the 11 operations per second. And that's related to this fundamental RC delay, some energy consideration, but there is certain limit. We are hitting the wall. We cannot process information faster with electronics than a certain speed. And with photonics, you limit only by the carrier frequency, which is 10 to the 15, the optical frequency. So it's like 10,000 times faster, but typical dielectric elements are large. Like optical fiber, we remember it's like for, it's tens of microns in size. So in the idea of this plasmonics is actually to take the advantage of both worlds, the speed of photonics and the size of electronics, and create something which would be as fast, or at least close to this as photonics, and use elements as small as in the case of electronics. So that's the whole idea of plasmonics. And to enable this, we use this surface plasmon resonance. That emphasizes the importance of this. And we actually distinguish two types of plasmon resonances, so-called localized surface plasmon resonance, when you have a tiny structure, like in the simplest case, it's just like a metallic ball, and as it's shown in these pictures, when electrons are displaced, you have this restoring force, and electrons will start bounce up and down, and that's what in the heart of this surface plasmon resonance. And the resonant frequency would depend on the size and on the shape of these particles. By controlling the shape or size of these particles, you control the plasmon resonance. And the confinement of light in this case are defined by the size of the particle, which could be small, 10 nanometers or even smaller. The other example of this localized surface plasmon resonance, it's like bow tie non-antenna, when I have two metal pieces, small ones. And actually, in this case, energy largely concentrated between the metal, in the gap, in the dielectric gap. And there is a big area related to this, like optical metasurfaces, which we'll be speak about a bit later, which consists of many of such non-antennas. And basically array of such antennas. And they have collectively a very different properties in terms of interacting with light. And that's arguably one of the most exciting development now in the area of metamaterials, when you're dealing with an array of non-antennas placed on interface between two different materials. That whole area is called optical metasurfaces. And the other class of this surface plasmon resonance is propagating surface plasmons. Either the metal dielectric interface, we already considered this surface plasmon polar return, and we derive this dispersion relation, how frequency depends on the wave vector, Or the other manifestation of these propagating surface plasmons is this metal insulator metal waveguide, when actually the wavelengths of propagating surface plasmon polariton could be much smaller than the wavelengths of light in free space. And that defines the confinement actually in this case. So the size of this insulator between two metals could be very small, going down to, again, 10 nanometers. And that's what defines confinement in this case. And remember, that's why they call sometimes this surface plasmon polariton as X-ray with optical frequencies, because frequency is optical, but the wavelength is very small. So, and again, that's, I would not go into further detail, but this electrical metamaterials or plasmonics, in this case, you control coupling to the electrical field component. They are important in the context of bringing light down to nanoscale, which is in the heart of nanophotonics. We will look in far more detail what kind of nanophotonic devices you could do by applying this concept. But for now, we realize that when epsilon is negative and mu is just 1, you could develop the whole field of plasmonics. And in the heart of plasmonics is confinement of light, bringing to down to nanoscale, either using by localized surface plasmons or propagating surface plasmons, which we call surface plasmon polaritons, two different classes. How exactly you could do nanophotonics, what kind of devices you could do with this, we would look into this later. So, but they're important. This is electrical metamaterials, or which define the area of plasmonics. Now look at the different quadrant when we create materials with negative mu, or positive mu for that matter, because at optical frequencies, as I said, mu normally equals to 1. To create anything different from 1, that means that you create artificial material or metamaterial. So when you, after coupling to the magnetic field component, you say this is magnetic metamaterial. So basically it implies that we are working with this or this area, when actually mu is different from 1, even though I'm showing here it's specifically negative. But as I pointed out, when you make it different from 1, you already speak of magnetic metamaterial. So, but in the end of the day, we are trying to look at this magnetic metamaterial in the context of negative refractive index, where actually you need both epsilon and mu negative. So how to make epsilon negative? We know, just take a metal. Epsilon is naturally negative there because of the existence of free electrons, they always move in such a way that they expel light from material, and that's why the negative is epsilon. So there are naturally occurring materials with negative epsilon. As for negative mu, we have to create these materials. So, and that's all for the, as I said, that's what you will see it in a moment, that would eventually enable negative refractive index materials. But before I move in further in this direction, let me provide few historical remarks. So quite often in the history of science, things which we developed look so brand new, so exciting, so revolutionary. But in many, many cases, there were scientific giants which thought about this quite often decades ago. But it happens so that they do this a little bit ahead of the time, meaning that at that time it wasn't really properly appreciated. The technology was not ready to develop it further. When it comes down to negative refractive index, it sounds so unusual, so revolutionary. But the thing is that as early as in 1904, it's even hard to believe, it's so many years ago, Sir Arthur Schuster, who was German but spent his research career in Manchester, UK, he actually wrote a textbook which he would not call, where he actually considered this negative refractive index. And but the funny thing, he would not call it like nowadays we would do modern optics or advanced optics, because he would introduce such a counterintuitive concept of negative refractive index. But he would call his textbook Introduction to Optics. I just saying all this, you would appreciate the modesty of scientists working so long ago. I'm not saying it's bad. I mean, we have to actually package our research in the best possible way, to excite a broader community, to make sure it's properly funded. That's normally nowadays research develops, whether we like it or not. But still, it's hard not to appreciate how people would make such significant breakthrough and would describe them with such modesty. And actually, Sir Horace Lamb also did some work very related to this around the same year, 1904. So they looked at all type of waves, including light, when energy propagates in one direction, whereas phase in the opposite direction. Remember, refractive index defines the phase velocity. Basically, it says by which factor phase velocity of light in the material is smaller than it compared to vacuum. And if a refractive index negative, it means that the phase actually propagates in the opposite direction as compared to the direction of propagation of energy or Poynting vector. So when phase propagates against the energy propagation, then we speak of this negative refractive index. And these two people actually certainly looked at this type of waves, and they knew about this. Another guy, Mandelstam, and as early as 1944, it's actually great former Soviet Union optical physicist. I should mention that he independently discovered what we call now Raman scattering. And it's really independently, and really at the same time, they published their papers, Raman in India and Mandelstam in former Soviet Union. And he described it actually very nicely, pretty much using the language we use it now. But again, it was a quite modest scientist, meaning, I mean, as a person, and but great scientist. And out of respect to him, actually, in Russia, they don't call it Raman scattering, they call it combination scattering. So, because he should be given credit. He independently and at the same time discovered a very important type of optical scattering, what we call Raman scattering. But in his lectures at Moscow State University, you could see in his pictures where clearly he described this negative refractive index. Yet another example when people actually knew about this that early. And these two gentlemen, Victor Vesilaga and Sir John Pendry, they actually are nowadays protagonists of this of the field of metamaterials, and they contributed tremendously in the development of this field. Vesilaga, in his seminal paper published in Russian in '67, which was translated in '68, actually was the first one who pointed out to have negative refractive index, you have to have material with both epsilon and mu negative. And Sir John Pendry also contributed a lot. He suggested this SUPERLENS, which allows this imaging with super resolution, which pretty much was like a starting point for the whole field. People got really excited about this. And later things like electromagnetic cloaking. So they, by the way, they both visited Purdue at different points for different events, and I know them closely, and in some cases we collaborate, like with Victor Vesilaga, two truly brilliant scientists. So I already showed you this equation that refractive index is square root of epsilon mu. It turns out, if you do a little bit mathematics, that the necessary condition for material to have negative refractive index is formulated by this inequality. And since modulus is always larger than the real part, you could immediately conclude from here to have negative refractive index, you have to have both epsilon real part and mu real part to be negative. What it would mean if refractive index is negative? It's actually interesting. Let's look at the conventional Snell's law, or Snell's law. When light is inserted in the interface between two different materials, it gets reflected and refracted, as it's shown here. But if refractive index is negative, the light, the sign of the angle should change along with the refractive index, and light would go the other side with respect to the normal. Because in Snell's law, you would change the sign of refractive index, but you also have to change the sign of the angle. So it would go in this direction as opposed to this. But more importantly, actually by far more importantly, not only it goes the other side of the normal, but the phase counter-propagates the energy. You see, this is where the energy goes, this is where the phase propagates. That's actually what makes negative refractive index. Actually, there are some special cases with crystals, with strong birefringes, when a beam could go the other direction with normal. But in this case, you don't speak of real negative refractive index. The real negative refractive index is you have when phase counter-propagates the energy. That's actually really important. So we need to have both mu and epsilon negative, the real parts. How to accomplish it? To have negative epsilon, we know how to accomplish negative mu. And this is the structure which was proposed by several groups actually, but let's consider the idea how to make negative mu. Let's say we have two metal strips, as it's shown here, separated by dielectrics. Pairs of strips, an array of them with a dielectric in between. And if you now irradiate with light, normal to this structure, as it's shown here, so that the magnetic field penetrates through pairs of these metallic strips. Since magnetic field oscillates, varies in time, the magnetic flux going through these metal strips also varies in time. But when magnetic flux varies in time, according to the Faraday's law, there should be electromotive force and there should be current loop induced by this time-varying magnetic flux. All right? So basically, the time-varying magnetic flux induces a loop current in this structure. So it's actually somewhat unusual current because, of course, here within the metal structure, you could think of this as a conventional ohmic current, but here you have dielectric. The thing here to appreciate that at high frequency, the displacement current, this term in the Maxwell's equation, dd over dt, is proportional to frequency. When you take this derivative, you would have omega epsilon e, right? The higher the frequency, the higher the displacement current. And normally, the contribution from this displacement current doesn't play much role at low frequencies, but at optical frequencies, it's very important. So you could think of this loop current as the conduction current within the metal strips, which is closed by the displacement current. So here again, because you have this time-varying field, dd over dt would give you this displacement current, and this conduction current within the metal strip is displaced by, closed by the displacement current. Another way to look at this is like LC circuit, where metal, and in metal we have negative epsilon x as inductance, and whereas dielectric where epsilon is positive, x is a capacitance. So it's like LC circuit with the resonant frequency, which depends on the shape of the structure. And the important thing is it operates at optical frequency. It's actually a very straightforward idea. It's surprising why people didn't look at this. That at optical frequencies in such a configuration, you would indeed induce this loop current. And when you do that, of course, you create magnetic moment. So that's the idea how to create the magnetic moment. And in the electrical field here, so would be just in parallel induce the conventional electrical response. So, and we know that metals have negative epsilon anyway. So when you have this pair of strips, which induces the magnetic moment, and if you put perpendicular pair of strips, in this case electrical field directed along these strips, that would provide you negative epsilon. So again, this electrical field in these strips induces negative epsilon, whereas this magnetic field induces negative mu, and by placing them together, you have a fishnet structure, which has both epsilon and mu negative. That structure was first suggested by Steve Brook in 2005, and that was the structure which was used quite often to obtain negative refractive index. And if you look at the very first experiments where people demonstrated this negative refractive index, in the microwave, of course, it's much easier to do. David Smith at that time at the University of California, San Diego, you'd use these so-called split-ring resonators, which provide this negative mu, and wires, which provide negative epsilon, and altogether they obtain negative refractive index. This is our structure, which we developed here in Purdue in 2005, and that was the first demonstration of negative refractive index in the optical part of the spectrum at 1.5 micron. That was done in parallel with the experiment done by Steve Brook at University of New Mexico, who used this fishnet structure. In our case, it was pair of rods, parallel rods, which support this magnetic response and electrical response, and altogether have negative refractive index. This is later more advanced structures when you have an array of fishnets, like it's shown here, and or array of these split ring resonators. And this type of more advanced work was done by Shang Zheng at Berkeley and Harald Giesen at University of Stuttgart. So that's I should say very challenging to do, and still challenging, but at least in principle you could have a material which have magnetic response at optical frequencies, not only magnetic response but negative magnetic permeability at optical frequency, and moreover negative refractive index. And let's a bit speculate what actually kind of interesting things you could, these materials would be characterized when they interact with light. As I already showed, with conventional material, when light is refracted, you have this type of situation. When light after refraction goes the same side with respect to normal. Whereas in materials with negative refractive index, it would go the other side with respect to normal. It's actually quite unusual and interesting. And it's a classical example which Ortwin Hess from UK showed. So if you look at the straw in the water, if water would have negative refractive, normally you have this type of image, a straw. It's like a broken, because refractive index of water is higher than of that of air. If water would have negative refractive index, actually a straw would look like this. So it's kind of interesting to train your imagination how the world would look like, or how would conventional objects would look like if materials, for whatever reason, would have negative refractive index. So even more striking example, when you look at objects inside of water, like a pond. So normally fish looks somewhat closer to the surface than it's in reality, because again, refractive index of water is higher than in air. It's very easy to show that the image would be closer to the surface of water. If water would have negative refractive index, actually you would perceive it that fish is floating above the water. That's pretty much interesting. I mean, that every time when I have something which, let's say, excites your imagination, there is a big chance for nice application as well. So don't overlook this interesting physics, unusual physics, because it always gives a chance for interesting applications. And in case of negative refractive index, such driving applications actually has been the idea to image objects with resolution beyond the diffraction limit, as was first proposed by Sir John Pendry, actually, in his revolutionary paper, when he showed that if a lens made of material with refractive index equal -1, in principle, you could see details of objects smaller than the wavelengths. Here you see the conventional microscope, which is indeed diffraction limited. We know that there is a way to see details smaller than the wavelengths using this near-field scanning optical microscope. When you have a tip much smaller than the wavelengths, you put it in close proximity to the object at distance smaller than the wavelengths. But in this case, you don't get the whole image. You just do it piece by piece. Sequentially, and it's actually very slow, even though you could see details smaller than the wavelengths, but you cannot get the whole image with resolution better than the wavelengths. So that's the way the conventional refractive index works. If your slab of material made of negative refractive index, instead of being refracted like this, it would be refracted like this. So if this ray goes like this, normally it would go there. But since refractive index negative, it goes here. So, and you actually have first re-imaging inside of this material and the other outside of this material. And as Pendry showed, actually, in principle, you're not limited by the diffraction the diffraction resolution in this case. The reason you have this diffraction limit, if you look at the Fourier component, if you have an object which has details finer than the wavelengths, the wave vector for these details would be larger than omega over c. And the propagation of image, actually, or information is described by this omega over c squared minus wave vector for those details. If wave vector is larger than omega over c, you have this exponential decay, meaning that all the Fourier components which bear information about details of your object finer than the wavelengths are exponentially decaying. You lose that information. Therefore, when you look at objects, you see details larger or comparable than the wavelength, but not smaller ones. Those are exponentially decaying. As it was shown by Pendry, in the material with negative refractive index, those components which have those Fourier components which have wave vector larger than omega c and exponentially decay when they propagate in air, within this slab are exponentially enhanced because you hit this actually, excite these surface modes. And as a result, you first loosen it, exponentially decay, then exponentially increase, and then here you completely restore the image with, in principle, perfect resolution. But the thing to point out here, every time when you have something exponentially decaying and exponentially increasing, it means that such a device would have exponential sensitivity to any deviation from the strict requirement. Like in this case, you have to have this n equal -1, meaning no imaginary part for all the frequency exactly equal -1. Slight deviation, and you would have exponential sensitivity to that deviation. Because of that, this type of lens does work in the near zone, but for the far zone imaging, actually, it doesn't work. Not because it's fundamentally impossible, but because it has this exponential sensitivity. Anyway, but that's actually resulted in lots of excitement, and people jumped into this area of metamaterials because the idea that you could, for example, image such small objects like DNA or viruses, which are not possible with conventional microscope because they are much smaller than the wavelengths, that's indeed excited very much the community. And later, our colleague, actually, Professor Narimanov in Purdue, suggested a little bit more, I would say, a SUPERLENS with more relaxed requirements. It's actually, they call it HYPERLENS. Nader and Getter from University of Pennsylvania independently proposed the same structure. The difference here, actually, that you could image not only in the near zone, but also in the far zone, because you adiabatically convert these modes which normally exponentially decay into propagating modes. I would not go into details, but that's a so-called hyperlens. A hyper here not because of the hype, but because of hyperbolic dispersion relation which you have in this case. He showed that this type of lens provides sub-wavelength resolution in the far zone as opposed to the conventional SUPERLENS proposed by Pendry, which because of this exponential sensitivity normally has this super resolution only in the near zone. Anyway, that's kind of important development as well. And I should say, even though it didn't become a technology, it hasn't become a technology like this SUPERLENS or HYPERLENS, but it certainly motivated the field. And many other devices actually came out of this field. Even though the original idea of this SUPERLENS was the driving force, the motivation. That's quite often happens to technology. You need to have something which grabs the imagination. In the end of the day, not necessarily that particular applications would work, but that would drive the field. And that's certainly the case for the field of metamaterials. This is some experimental realizations of this HYPERLENS done by Shang Zheng, whom I already mentioned from University of California, Berkeley. And this is some development which we proposed here, still not realized yet. Basically, you could have some small features which are placed to each other closer than the wavelengths. You cannot see them with conventional microscope. You place here HYPERLENS, you increase this magnifying HYPERLENS, you increase the separation to the extent that it becomes comparable to the wavelengths, and then you use conventional optics to see this object which are originally much smaller than the wavelengths. All right, so let me stop here, and next time on Wednesday we would consider this transformation optics and specifically clocking. That's actually a very exciting development related to the field of metamaterials. Questions?